Good morning everyone. Welcome to the third video on relativity for the IBDP physics curriculum. And in this video, we'll be exploring more on the relativistic effects. So there are three relativistic effects which we have considered to be discussed in detail. The first one is time dilation, and second one is length contraction, and the last one is simultaneity. So how do you apply whatever you have learned so far? Like, for example, you have learned Lorentz transformations or Galilean transformations and so on. Okay, how do you apply it to these one of them, and which ones are applicable? Okay, and what are the effects of it? That's what you are going to learn about it. Okay, so towards it, now let us first understand what we have learned in the previous chapters, in the previous videos. In the first video, we had learned about Galilean transformations, as you have seen there. We have seen that x dash equal to x plus vt, y dash equal to y, and z dash is equal to z, and t dash equal to t. That means only the x dash was changing, okay, or the x coordinate can be located or could be figured out from the stationary frame as seen in the moving frames. And then we also saw about the additive formula for the velocities. Okay, and then this is nothing but what you have already learnt in your relative velocity and other concepts as in mechanics. There's nothing special about it. The next thing is about, we learned also at the end of the video about why this kind of transformation equations is not applicable when we look at particles which are moving with velocities nearly equal to velocity of light. And then we look for, there should be a change over it, and this change was brought in by looking at the transformation, which is by Lorentz transformation equations. And in Lorentz transformation equation, we looked at how these coordinates will change by the introduction of a Lorentz factor gamma. Okay, and then we saw that the x coordinate as observed in the moving frame is given by x dash equal to gamma into x minus vt, as you see there. So those were the equations. T dash was also changed, y dash and z dash remained the same. The reason is because the particles were moving in a one dimension. And as usual, when we start looking into it, we also saw that the velocities in the moving frame for a particle was seen to be u minus v divided by 1 minus uv by c square. This did not follow the velocity additive addition as we have seen in the Galilean transformation. So there was a change over here. Now what we are going to do in the next few slides is that we are going to apply, or we are going to consider how these can be changed, or how this can be changed in such a way that you can find out, okay, the length, time, and simultaneity. So in the two different frames. Now let us begin with this. Okay, now the proper length and proper time. This is something which we have to define first. The proper length is nothing but the length of an object and the time interval if an event changes when observed in frames that are moving relative to an object. What does this definition mean? Let us say, for example, I want to find out what is the length of this object. I am sitting here, I find out the length of the object. This could be around, let us say, 20 centimeters. Length of this pen is 20 centimeters. Okay. Now let us say, for example, I am moving in a train, and you ask me what is the length of this object. The length of this pen, once again, for me, will be 20 centimeters. But for a person who is standing outside, the length should be 20 centimeters for lower velocities, while if the train is moving at a much faster speed, in that case, the length would be changing. Okay, that's first thing. This is called as a proper length. So proper length is nothing but the length of an object relative to the observer. Okay, if the object is also moving, then the observer should also be moving with the same velocity. That means with respect to the object, with respect to the observer, the object should be at rest. This is, in such cases, whatever length you define, that is called as a proper length. In a similar way, what is meant by time? Proper time. Proper time means whether I am at rest or whether I am in motion, whatever is the time recorded in my watch, this is my proper time. Okay, so therefore proper time is relative to an observer. Okay, only with respect to an observer we define a proper time. The proper length and proper time are being defined by the values L0 and T0. Okay, now let us move on to the next one. Now, how do you simulate a proper length and proper time? Let me show you an example in the next slide shown here. See, for example, there is a clock here. The clock shows the time T0, okay, as recorded by a stationary observer. Okay, the clock goes around one full circle, time recorded is T0, maybe 1 second, 1 hour, 1 minute, whatever it would be. In a similar way, let us say there is a person in a train, and this person is now recording a photon which is getting reflected from one mirror to other mirror, and it is traveling all the time, all the length, complete the width of this carriage, and coming back to the same point. Okay, whatever is the time taken is recording that as proper time t. Okay, and then whatever is the distance traveled by it, that is equal to L0. So we are imagining that the observer is not looking anything outside. He's just looking at the clock. He is looking at what is the distance traveled by the photon from one point to the other point. We are not considering the motion which is happening outside. This is a normal thing which we do every time, right? When you're traveling in a train, for example, I throw a ball. Okay, I don't assume that my train is moving at 100 km per hour. I am also throwing at the ball at 10 meters per second. Okay, that means the total speed of the ball is 100 km per hour plus 10 meters per second. I don't do it. I will only say my speed of the ball was only 10 meters per second. To an external observer, the speed could be different. Okay, so there we were coining only about the speeds in the Galilean relativity. Now what we are looking at is we are looking at the time also. What is the distance traveled by? That's what we are now looking at. Okay, now let us move on to the next one. Now what we do is, let us understand more about time dilation, the first phenomenon that we have. When objects travel close to the speed of light, to an observer moving relative to that object, it looks as if the object has slowed down. So this is what it means. Okay, now let us understand what does it mean actually here. Now, you see, for a person who is standing on the earth, is a stationary observer, he is having a timer, he watches the time. There is a person who is standing in the spacecraft. Okay, she is also moving with a watch. Okay, now you find out, let us say the time taken by the spacecraft, according to me, I am a stationary observer, to move from point A to point B, let us say it is equal to 1 year for me. But for the person inside the spacecraft, it appears it is slowed down. It could be something like only 7 months. Now you may be asking, how is it possible? Whatever is the time, according to me, the same time should be seen by them also. Why is it 7 months for them and why 1 year for me? That cannot be possible relatively. Okay, now let us see this with an example with a simulation. Okay, shown here is a time dilation experiment over here, which shows that there is a person in the spacecraft. So this is taken from this website, javalab.org. I had already put the link in the description. You can look into it. And then this is the time over here. The speed of the spaceship can be adjusted over here. And there is a slider here to adjust it. And you can click on run over here. Okay, when I click on run and I say the spaceship is 0, speed of the spaceship is 0, click on the run over here. Now what do you observe? EX stands for the external observer and this is for the internal observer. There are two mirrors kept over here. These two mirrors, how does it act? There's a photon which is being sent from here. It goes all the way along, hits this mirror, and thereby it takes a time of 1 second. Right? So what is the proper length? This is my proper length. What is the proper time? This is my proper time. The proper time is 1 second according to an observer inside the spacecraft, and also to an external observer also it is only 1 second. See, that values are matching because the spacecraft is not still moved over here. Now what I do is I will increase the speed of the spacecraft. Instead of 0.10, 0 times the spacecraft not moving, I will make it a 0. Let us say 2c. 0.1, 0.9, 19, 0.2. Okay, I'll keep it as 0.2c. Let me restart this experiment. See, this is 0 here, this is 0 here. When I run this, as you observe, the photon is now trying to go, but it is not going in a straight line. Why is it not going in a straight line? Okay, I can see there is a dotted line here. Okay, and here you see this has taken 1 second to reach this mirror, but here it has taken 1.027 seconds. Why? What is the reason? Because for an external observer, since the spaceship is also moving, we always see this that the photon is not moving in a straight line, but the photon is now taking a diagonal line like this, right? So as it is moving, it appears that it is moving in a diagonal line, and as a result of it, the timer for us also shows it has taken a longer time. But for the person who is staying inside it, what's happening? Both the mirrors are moving simultaneously, and he considers that the photon is moving in a straight line, and he looks at the time and it says that's only 1 second over here. So this is my proper time and this is my apparent time. The time in the stationary frame is my apparent time and the time in the moving frame is the proper time. Now let me expand this one. Let me increase this. Let me make it as 0.5. 0.5c. Okay, in that case, let me see what happens over here. When I click on the run button, I observe now the photon takes a much more longer diagonal path, right? And then you see the time taken by here is seen to be almost around, so here it is 1 second, proper time is 1 second, but this time is seen to be 1.155 second. What does it tell you? That means the time has increased over here. The apparent time is increased. Okay, the person who is moving in the normal frame, that is in the lab frame or in the spacecraft frame, for him it is only 1 second, but for us it appears that it's 1.155 seconds. That means the time has been larger for us, right? And why is it larger? Because we see that he has not moved in a, the photon has not moved in a straight line, but the photon has taken a diagonal path over here, right? So what has elapsed for the person inside the spacecraft is 1 second. For me, it has become 1.155 seconds, right? Okay, let me increase this to 0.8 C, much more larger, right? 0.8 C, right, 0.8 C. Let me run this. Now what do you observe? So it has taken a much more larger deviation, right? You see, the photon is taking a much more diagonal way, and the time taken by it, it has already crossed 1 second for me, but for the person inside the spacecraft, still it is going on, right? It is 1 second for it, right? Which means here I have created 1.667 seconds, nearly 67% of it more, 167% of it I have seen, but for the person inside is 1 second. That means for me, the same duration, it appears that it has taken a much longer time over here, right? Okay, let me make it as one more. Let me make it as 0.9 seconds or 0.96 seconds. 0.96 times the speed of light. Okay, now let us click on the run button here. We have kept it at 0.96. Now, as you see, the photon now moves with a much longer diagonal path, okay, as compared to all the previous cases. Okay, I think you would have watched the movie Interstellar. In movie Interstellar, what you can see, the astronaut, he goes on to the space, and while he returns back from the planet after the interstellar journey, he finds his daughter to be something like around 85 to 90 years old, been in the bed, right? So you have seen this one. So if you want, I can just play this movie after this clip. Okay, now before that, okay, let us see here. See, in the proper lab frame, it is 1 second, while in the external observer, that is on the earth, it is 3.5 seconds. Which means if it is something like, if the astronaut has taken 16 years to take a roundabout journey, then here what would have happened? It would have been 16 into 3.5. How much will it be? 16 into 3 is 48. 48 plus 8 should be 56. So his daughter would have been 56 years older than whatever she was existing. So if suppose initially when he went, he was only something like around 8 years, then 8 plus 56 should have been our age, right? 64 years. Okay, in a similar way we can see this. So let us go back to the clip and watch, okay, the exact part of it.
You told him I like farming. It was me, Murph. I was your ghost.
I know. People didn't believe me. They thought that I was doing it all myself. But I knew who it was. Nobody believed me. But I knew you'd come back.
How?
Because my dad promised me.
I'm here now, Murph. I'm here.
No. No parent should have to watch their own child die.
Okay, now let me go back to my screen and show you what is the mathematics which we need to do it. Now, as you see, the same experiment over here. So you have two mirrors kept here. There is a one photon which starts from here. This photon strikes this mirror, comes back over here. So by the time it comes back, it is nearly 1 second. It's exactly 1 second. So you see, every time it hits here is 1 second, 2 seconds, and so on. The timer gets on like this over here. Now what we do is we conduct an experiment like this. The experiment is that you have the same kind of timer present in a train, and as well as you have it in the train and as well as a stationary observer. Okay, when the train is moving, what do you observe? You observe that the photon undergoes a zigzag path. Okay, if you want, I will just go back once again and I'll show you this. Okay, so now it is moving on like this. Okay, now you see that there is a person standing in the train. The same timer is present in the train and as well as the stationary observer. As the train starts moving, what do you observe? You see, as the train starts moving, the photon, the photon now undergoes a diagonal displacement as seen by the person observed outside the train, right? So that's what is seen. So in other words, shown here is an extended view which shows the photon according to stationary frame goes straight like this. But the photon according to the observer outside goes in a diagonal path like this. And we know this length would be larger than this length over here. Let us consider this distance is L, this is distance D, and this is V delta T between the positions of mirror 1 and mirror 2 over here. Okay, that means it takes a time delta T to start from position 1 and to reach a position 2 over here. If I have a timer here, if I have a timer on the stationary frame, then definitely the time taken by the light beam to start from position 1, go to the mirror and again come back to the position 2. Okay, it is like this. Let us say the time taken by the mirror, the time taken by the light beam photon to start from here, go to mirror 1 and come back to mirror 2. That is, come back to, this is mirror A and this is mirror B. Okay, mirror B, go to mirror A and once again come back to mirror B is nothing but, let us say this is your delta T0. I will assume this is delta T0. Okay, if it is delta T0, I can now write this as a distance by velocity. What is the velocity? C over here. Why C? Because the velocity of light. I will put this one like this. Okay, so thus I have delta T0 is equal to L by C. Next, what I can do, I want to find similarly for the value of D also. Now what I will do is, the photon starts from position B, okay, goes to mirror A and comes back to mirror B once again at position 2, okay, undergoing a path D plus D over here. So I can now write delta T is equal to total distance traveled 2D divided by the velocity at which it travels over here. Okay, so what is the velocity which it travels? This is nothing but C only, because the velocity is not changing. It is not undergoing something like refraction and so on. So it is the same C. So delta T should be equal to 2D divided by C over here. Now what we do is we use Pythagorean triplet. Okay, so this is my D, this is my L, this is my V delta T divided by 2. V delta T divided by 2. Okay, now what do we have? Pythagoras theorem tells you L square plus V square delta T divided by 2, the whole square is equal to D square. Let us substitute all of them. From here, what can I write? I can write L equal to C delta T0. Is it C? No, this is L here. This is starts from L, goes upwards, comes back. That means it's 2L over here. I'm sorry. This is 2L. So this should be, L should be equal to C delta T0 divided by 2, the whole square, plus, now this one I will retain like this, V square into delta T by 2, the whole square, is equal to D. What is D here? According to it, D is equal to C delta T divided by 2. C square delta T divided by 2, the whole square. Now you see 2 is present in all the terms, so I can cancel them as well. So I can now write C square delta T square, delta T naught square, plus, I'll write T naught properly, plus V square delta T square is equal to C square delta T square. Now rearranging the terms, I can now write C square delta T0 square is equal to C square minus V square into delta T square. I can write like this. Now what do I need? I need delta T here. Okay, what is delta T? The time taken by the train to move by the mirror to move from point 1 to point 2 here. Okay, so I will now write, I'll do the space over here. I'll do it here. Okay, I'll do it here. I'll do it here. I'll write delta t is equal to, is delta t square is equal to c square divided by c square minus v square into delta t naught square, or I can now write delta t is equal to, here I'll simplify it one more step over here. I'll write 1 into delta t naught square divided by c square minus v square divided by c square. I'll write like this over here. I have brought this c square downwards. So I'll take delta t, I'll take the square root on both the sides, which will give me delta t divided by, now you see c square by c square is 1 minus this v square by c square. V square by c square, and you see I took root here, I took a square here, cancel this square, so there should have been a square root over here, so therefore this should be square root of something over here. So now if I consider this as gamma, I can now write this as delta t is equal to, what is this now, is delta t0, I missed the 0 here, is equal to delta t0 divided by gamma, right? Delta t is equal to delta t0 divided by gamma. What does it tell you now? It tells you that the time that you measure in the stationary frame is equal to the time that you measure in the proper time divided by gamma. What will this gamma be? Gamma will always be less than 1. Do you agree? Because you see, you get 1 minus v square by c square, no? So no particle can travel at the speed of light except a photon. So as a result of this, this v will always be less than c. If this v is less than c, this negative, whatever you have here, this will be less than 1 over here, right? This will be less than 1. If this is less than 1, okay, I'll write it down here. If gamma is less than 1, then automatically 1 by gamma should be greater than 1. 1 by gamma should be greater than 1. In other words, your delta t should be greater than delta t0. That's what we had seen earlier also, right? So when you have a spacecraft moving with a speed nearly equal to speed of light, what did we see in the simulation? We saw that the time taken by the spacecraft would be lesser to travel a given distance, while the person on the earth will feel that the spacecraft has left a very long time. That's what I told you as an example, right? Now let us understand some questions over here. Now, why doesn't the light beam hit the mirrors fast when the train is moving? Okay, very simple question. No need of any mathematics. You can just think and answer this. What is the answer for this? See, why do you consider this question? I consider this question because when you have a light beam starting from here, it goes and hits over here. Since train is also moving, it should actually push it faster, right? It should come and immediately hit here. Okay, so why don't I see the light beam hits the mirror fast when the train is moving? The reason is because the velocity of light is seen to be a constant in any kind of frame. What does this tell you? It is from your second postulate of special theory of relativity, right? So it says that speed of light, where is my pen? It's not being seen. Okay, speed of light, the answer for it is speed of light is same in all inertial frames. Is a moving frame an inertial frame or not? It's definitely an inertial frame, right? Okay, let us move on to the next question. If speed is same, is distance moved by the photon same for the stationary observer? Now, what is that you said? Speed is same. Okay, c1 is equal to c2. This is your stationary. This is your moving frame. Okay, if this is stationary, same. Okay, then see, photon has started from here. It moved all the way along and came back over here. Speed is same. Okay, but the time is different. When the time is different, now you know c is equal to distance by time taken. Speed is equal to distance by time taken. Now for a stationary frame, if time is increasing, then what should distance be? Distance should also be changing there, right? So we should now look for it. Okay, so therefore, if speed is same, is distance moved by the photon same for stationary observer? No, definitely it is not same. Let us look at, okay, what is happening to the distance moved by the observer, distance moved by the photon according to the stationary observer. Okay, now let us solve this problem to understand what we have learned so far. Ethan spacecraft is traveling to a nearby space outpost at a speed of 0.9 c. Let us write down the spacecraft. This is the spacecraft. Let me write E for Ethan, and this is now moving with a speed of 0.9 c. Okay, Mia is stationed at the outpost that is rest relative to the base station. So from here, she is standing over here. This is Mia over here. And according to Mia, distance from the base station to the outpost is so much. So this distance is seen to be 0.02466 light years. Show that Mia measures the time taken for this journey to be approximately 10 days. And that it's not my, here it should be by. By the time traveler is 4 days. You see, 10 days here, 4 days here. Which one could be your proper time? Which one could be your apparent time? So this could be your proper time. This could be your proper time. Okay. Proper time will always be lesser than apparent time. Okay? That's how you can identify it. And this could be your apparent time. So first let us find out apparent time. So apparent time, how do I find out? Time t is equal to, what is this distance? 0.02466 light years divided by 0.9 c. What I'm going to do is, I need the answer in terms of days. This is light years. So I need to convert this into a distance. So what I do, so I will convert this as 0.02466, and light year is nothing but speed multiplied by time, right? What is the speed here? C. Light travels with that speed multiplied by time. What is the time here? 1 year. So I'll write this as 365 days divided by, considering this not to be a life here, right? So divided by 0.9 c. When I do this c goes away. So I'm left out only with this value. When I do this calculation, let me do the calculation, open my laptop, open my calculator, 0.02466 multiplied by 365 is equal to 9 by 0.9 is 10. Okay, so thus I get the answer here as 10.001 days, or which is nearly 10 days. 10 days. You got the right answer. Next, what is the thing? Now, what is this? This t we have got. Now we want t naught over here. So now what is the expression? The expression is t is equal to t naught divided by 1 minus root of 1 minus v square by c square. Okay, what is v here? v 0.9 over here. Okay, let us substitute. This should be t naught divided by square root of 1 minus 0.9 c divided by c, the whole square. The c and this c goes away. So this should now be equal to, what is c naught? I do not know. That's what I need to find. T naught divided by root of 1 minus 0.9 square. What is 0.9 square? 9 square is 81. So this should be 1 minus 0.81, which should now be equal to T naught divided by, what is 1 minus 0.81? 0.19, root of 0.19. Now what I need? I need T naught. So what is T here? T is nothing but 10 days. 10 days over here. So therefore, let me write here, T0 is equal to 10 days multiplied by 0.19. When I do this, what is the answer I get? Let me go back. So I get the answer here as, a square root of 0.19 will give me 0.433 multiplied by 10. I get the answer as 4.35. 4.3. Since it's one significant figure, what I do is I can write this as 4 days. Nearly 4 days, right? So thus we are able to show both the answers. See, relativity theory problems are quite easier. But only thing is, you should know what is the logic, how to solve it, what is being given. Okay, hardly 3-4 problems are there, 3-4 formulae are there. Okay, you should know which formula to use where, and you need to identify the parameters. If you do it, automatically, easily, you can do one problem from here. It should not be difficult at all. Okay, all right. Now let us move on to the next topic, which is on length contraction. So what is length contraction? Length contraction is nothing but when you have an object moving with a relativistic speed, the person in the stationary frame would be able to see that the object is moving with the length of the object is seen to be much smaller. It appears to be contraction. See, whatever we define here, length contraction, time dilation, and so on, it's all with respect to a person who is standing on the earth, who is standing on a stationary frame, okay, and not with respect to a moving frame. Okay, so therefore, length contraction is nothing but a stationary observer sees length in a moving frame as shorter than in his own frame. Okay, that is what we call as length contraction. Now towards it, shown here as an example of a football, wherein the moment you kick this ball, you observe, okay, if it is at a normal speed, no issue, okay, you will be able to see it only as a spherical one. But if it is going at a relativistically higher speed, then what will happen? You can see the ball appears to be smaller and smaller. At one point of time, the speed of the ball is so higher, okay, nearly 0.960 and so on, it appears like a thin line, right? That's what happens. So this is what you got as a length contraction. Okay. So the length of an object is the difference in the position of its ends. Okay. It tells you what is the position. So if you look at this delta x over here, you can see delta x is equal to x2 minus x1, which is equal to L over here. You take an object in a moving frame, as you should see there. Okay. And this should be equal to x2 minus x1 from the moving frame. That means for a motion, for example, if I consider this object, it's x2 minus x1. This is my x1, this is my x2. I can easily say x2 minus x1. Difference between these two is equal to L. But an observer in the moving frame S dash, they measure the length of the rule as x2 dash minus x1 dash, which is equal to L naught. Why did I call it as L naught? Because according to me, I am the observer, I am moving along with the same velocity as the object's velocity, so which is equal to L naught. Okay. So now let us look at length contraction. Since the frame is moving at a relativistic speed, you cannot use Galilean transformations, right? Why you cannot use? Because relativistic the Lorentz transformation comes into play. So apply the Lorentz transformation for both the coordinates x1 dash and x2 dash. When you do it, what will happen? x1 dash is written as gamma into x1 minus vt, and x2 dash is written as gamma into x2 minus vt. Okay, this is what we have seen in the Lorentz transformation. If you remember, Galilean transformation failed, so we used the relativistic transformation, which is Lorentz transformation, by introducing a gamma factor, right? So therefore, if I subtract x2 dash minus x1 dash, I get this value, and thus I say L naught is equal to gamma times L, or L equal to L naught times by gamma. Since gamma is less than 1, L appears to be greater than L naught. The length of the object will appear to be larger than the original length. So that is what you will be able to see over here. Let us understand what we have learned so far. Okay, from here, a spacecraft departs a space station and travels towards a distant star system. The space station moves at a speed of 0.8 c relative to the space station. Okay, so you have, this is your spacecraft. This is your spacecraft, which is moving like this, and this is your 0.8 c velocity. The star system is 20 light years away, according to an observer on the space station. The proper length of a cargo attached to the space station is 600 meters. Calculate the length of the cargo bay as measured by an observer on the spacecraft. See, when you say 600 meters, how do you measure? You take an inch tape, measure the length. Okay, this is according to a stationary observer. Yes. So now when I say 600 meters, what is this now? This is your proper length. Proper length is L0 over here. What did I say? I said that L is equal to L0 gamma, right? This is the relativistic equation. Now, when I say the spaceship is moving at a velocity of 0.8 c, what I will do is, I will write this as L is equal to 600 multiplied by root of 1 minus v square. What is v square? 0.8 c. 0.8 c the whole square divided by c square. Okay, v square by c square. This c square and this c square goes away. You get 0.8 over here. So this should be 600 root of 1 minus 0.8 square is 0.64, which should be 600 root of 0.36, which should be 600 multiplied by 0.6, which should be how much this should be? 360 meters over here. Thus, the person on the spacecraft will now measure the length of the cargo bay to be only around 360 meters. Now, let us move on to the next one. Simultaneity is the third part which we will be learning. Let me share my screen. Okay, so what is simultaneity? So we already learned about what is your length contraction, what is time dilation. Now let us learn simultaneity. Whether two spatially simultaneous events occurs at the same time is not absolute, but depends on the observer's reference frame. Okay, so now I am showing you this particular simulation. Okay, so there's a person who is standing inside the cart. I will move the slider back to 0. Okay, which means what? So the cart is not moving, and there's an event which has been happening. There's a light source in the middle, and the observer measures the time to reach both the sides. Okay, there's a photon which comes out from here. One photon will come here, one photon will come here. Now let us look at it from the inside perspective. Okay, click on this one here. As you see, as a photon travels on either sides, there's a clock attached to this photon, and it is observed that inside person will be able to see 1 second and 1 second over here. Okay, so now let us look at outside one. Now there's an outside person. He is also able to see that it takes the same time 1 second and 1 second to reach outside. Next, what I do is, let me increase the speed to something like 0.2c, similar to that of what we did in time dilation. Now inside perspective, what do we observe? Now you see, this has taken 1 second, this has also taken 1 second, okay, simultaneous, and this is in the lab frame itself, because the clock is fixed, okay, along with the photon, and therefore you are able to see the same timings, okay, even though the cart is moving with this speed. Now let us look at the outside perspective. When I click on this, what do you observe here? You see the photon that has reached here. See, this is an external observer. The photon that has reached here, it has taken 0.84 seconds only. It has not taken 1 second, but this has taken 1.25 seconds, more than this, right? So therefore it is much larger over here. That means what's happening over here? So this takes a very longer time. So the outside observer is able to see this one quickly, and this he is able to see it at a later stage. Let us click it at 0.5 seconds, 0.5c, 0.5 the speed of light, right? I kept it over here. Inside perspective, same time, right? There's no changing time. Outside, it's much larger. Why does this happen? Now this has taken 0.67 seconds, while this has taken only 2 seconds it has taken, much larger. Why does it happen like this? Because you see, there's a time dilation and there's a length elongation over here. For him, it appears that, okay, the photon appears a much longer time, travels a much longer distance, right? Now let me keep this at a much, let us say at 0.8 times the speed of light. Inside perspective, 1 second both. Outside, see, it has reached so quickly, 0.56 seconds. But this you see, oh my god, it's going on increasing, went until 5.2 seconds, right? So after 5.27 seconds, it's what is simultaneous in one frame may not be simultaneous in the other frame. That's what we say, okay? So thus, you can see simultaneity also plays an important role, or it also can differ when we consider the frames moving with higher speeds. Okay, in one frame, it could be simultaneous. In the other frame, it could be in such a way, first event happened now, and after some time, the second event happened. Thus, simultaneity may not be possible in the moving frames, okay, if it was possible in the stationary frame. That's what we call a simultaneity. Okay, so with this, we come to an end to today's lecture, and the following takeaways are, we have seen that time gets dilated, the length gets contracted, and you see in each of them, the factor that is responsible here is nothing but your Lorentzian factor, right? Similar to that of what we have learned in the previous video also. Thank you once again for being with me. So tomorrow's talk, that is on Monday or Tuesday, this might be getting published. The reason is because some video editing which will be left behind. Okay, so if you have any more comments on this, you can definitely put it across. Thank you all for being with me for the complete time, and before leaving the video, do like, share and subscribe to my channel so that you can get more updates. In fact, I'm planning to do much more video lectures on the other concepts also. Thank you once again.